I'm always amazed when this thing works. Hey, good evening. It looks like we've got Phoebe so far. And that Phoebe, it's just you and me. Where's everybody? We got 3 minutes. We start our class. Are you driving on the road right now? Earth calling Phoebe, Earth calling Phoebe. Come in,
I'm
Phoebe.
here. I'm
Are
here.
you, are you driving or are you not driving?
Yes, I'm driving.
Uh-oh, be careful. You pay attention to the road. That's the thing to do. And we'll wait till our others show up here. But it's just you and me. If you had any question, go ahead and ask me.
I had a question.
Sure.
If we do the lab thing, does that exercise replace our lowest lab grade?
Yeah, sure. I think that's a good idea.
Okay.
We'll do that.
Okay, I was just curious because I
Yeah.
went to all the labs, but there was one I'm kind of debating whether I should do that on.
Yeah. I didn't put a due date on there. So I was just going to tell everybody to get that in as quick as you can so I can start adding things up.
Makes
But,
sense.
but yeah, we'll replace the lower. I don't think you have very many low scores on your labs.
I have one that I'm not so happy with, so I might as
Well,
well
yeah.
learn something while I'm at it.
Now, what I want you to do on that is to, you don't have to do the first one. I did that for you. You can read it on content, but I think there's 6 of them. So it looks like there's five different problems you have to do. And show me your impedance diagram and find the current for those other 5 circuits. And you'll have a makeup lab. How's that?
That sounds fine. Thank
Yeah,
you.
it's easy. You'll have no trouble doing that. And that's what you would have done. The beauty is that in the laboratory, you would have got to measure the current to see if it's the same as what you figured out on your calculator. You know, the theoretical is one thing, the actual is another. It's nice when they meet. But we were told not to get together, so we didn't get together. But we're coming to the end now. Tonight is our next to last meeting. Next Tuesday night, or I mean, yeah, next Tuesday nights. Oh, no, wait a minute. Yeah, that's right. Next Tuesday night's our last meeting, the last lecture. And let's put the homework on the blackboard here. Just a minute. Let me look that up. Your homework is homework number, well, let's see, which number is it? 14. It's homework number 15. And it's problem 1531. Oh, it's sad. That's your last, no, it's not your last homework. There's one after that. According to the syllabus, there's one more homework. So this is the next to the last homework. And when you turn in that last makeup lab, your labs are finished. And the final is a take-home final. We're not gonna do the final in the lab. It's a take-home final. and it will be available December 10th, which is Tuesday. Your final will be available December 10th, which is a Tuesday, and it'll be due. No. December 10th is not a Tuesday, it's a Thursday. And it's due, that's Sunday night, the 13th. It's due Sunday. Okay. And I'll get all the grades done and turn in the grades, and we'll be through with this crazy semester. Well, we need to get started on our tonight's work. I wonder if anybody else showed up. Gosh, it's just you and me, Phoebe, so I'm going to go ahead with my
okay.
class. Ready or not, here I come.
Okay.
But it'll be on YouTube. If you needed to watch YouTube, that'd be fine. Now, what I want to talk about is this business of RMS, the root mean square, so that we could understand it. It'd be nice to understand it. What it is you get the same power. Power in a DC circuit. We're pretty happy with that. We can do that. Power in a DC circuit is just equal to I squared R. It's equal to I squared R. Well, we have other V squared over R and I times V. They all give you the same power in a DC circuit. We could do an example. Here, let's do an example. There's that stuff there. It'll be on YouTube. You don't need me to write that. It's in your Blackboard stuff there. See, say you had a 12-volt battery. Okay, 12-volt battery. You know, that's like a car battery. Go open up the hood of your car, look at the battery, and say, hello, 12-volt battery. That's what that is. It's a 12-volt battery. And let's say you took it out of your car and hooked it up to a little electric heater. Basically, all an electric heater is just a resistor, and it gets hot. Now, sometimes they'll have a fan. Like I know a person that has an electric heater. They plug it in, turn it on. It's got several settings. And they connect there's current running through the resistor there. And you could run a heater like that. If you had a fan, you could take that fan and blow. See, that resistor will get hot. It'll get red hot. Have you seen heaters like that? They get red hot. And if you had a fan, yeah, it'll blow that warmth. Kind of nice to have down by your feet in the wintertime. And so the power, well, why don't we get the current? Here, we'll do a little DC stuff here. The current would be, I don't know. Let's say the resistor is 1 ohm. We'll make this easy. The current would be 12 amperes. And the power would be I squared R. Well, that would be 12 squared times 1. You know what that would be? That'd be 144 watts, wouldn't it? 144 watts. Well, that's kind of warmish. You know, a 60-watt light bulb, for instance, is pretty warm. If you had a 60-watt light bulb and you go over and you put your hand by it, it'll warm your hand up for sure. Well, this is 144 watts. That's more than twice as big as a 60-watt. Okay. So you got yourself a heater there. You know the current. Now you can get the power by going V squared over R. Let's try that. Well, I'll give you the same thing. It'll give you 12 squared over 1. We should have picked a different number, but it doesn't matter. You get 144 watts. And finally, power could equal IV. Take the current and times it by the V. And guess what? You get 144 watts, don't you? Okay. Now, the thing is, though, you don't want to take your battery out of your car and make your foot warmer run off your battery. You want to plug it in. Okay. Well, let's talk about power in an AC circuit that would give you the same heating. What we want an AC circuit that gives you 144 watts. And we want to have a 1 ohm resistor. All right, well, let's try that. Do you understand what we're doing here? We're going to convert this thing to an AC circuit. But see, an AC circuit, what it has is, well, we'll still keep the 1 ohm resistor. That'd be all right. But the question is, what kind of a AC source do you have there? Well, don't know. That's what we're trying to figure out. But see, with AC, the current goes one way and then it goes the other way. The current goes back and forth. You know what the current does. It does this. There you go. It's a sinusoidal current. But those electrons running through that resistor, even though they turn around and go back the other way, they warm that resistor up. They'll warm up the resistor all right. And we want them to warm it up and give you the same heating. We want it to give you 144 watts. Well, how are we going to do that? Well, they have an equation for power for an AC circuit, and it goes like this. It goes they call it the RMS current squared times the resistance. Now, or if you don't like that, you can go the RMS voltage divided by the resistance. Or if you don't like that, you can go the RMS current times the RMS voltage. You want them all to give you the same power, namely 144 watts. Okay. Well, if this resistance is 1 ohm, like we have here, what would be that? Let's do a little math here. 144 watts is equal to this RMS current times 1 ohm. So what do you get for the RMS current? Well, I get 12 amps. How about you guys?
I wish I could tell you, but I gotta watch the road.
I can't. I don't dare ask my students what they're getting because they're watching the road. Or you're watching the road, yeah. Yeah, be careful there. Well, okay. How'd I do there? Let's see. You take the square root, you get 12. You get 12 amps, but it's 12 root mean square amps. And let me show you what the current does in an AC circuit. Here's the current. You just have to watch this on your YouTube.
Yeah.
See, the actual power that you're getting varies. It's called instantaneous power, and it's I squared R. But the current is being squared. Now, if you square a sine wave, here's what you get. Let me see if I can draw that in a different color. You'll get, I don't like that color, forget that one. This red sounds pretty good. You'll get, I'm trying to square this current. You get, the frequency is twice as big, and it goes up to a maximum. Yeah, okay. Artist rendition of the power there. And see, what we want is we want an average current. Well, here's your maximum. That's your maximum current. And the minimum current is 0. And see, it goes up to the maximum, down to 0. But the average is right down the middle. Let me see if I can draw that. There we go. That's your average current, or, well, we call it the root mean square current because it's the square root of the mean of the squares. See, these are the squares. This is I squared here that we plotted up. And the mean of the I squareds is right down the middle. It's 1/2 of the I max. Let me write that down someplace. If you're driving and you don't see this, you have no idea what I'm talking about. But that's okay. That's okay. You have to do what you have to do. I understand you have jobs and things. See, the average current there is 1/2 of the maximum current. And that's equal to, okay, now what we want this, we call it the RMS current. It's equal to, well, that's the maximum current squared. Yeah, here we go. The RMS current squared is 1/2 of the maximum current squared, which is, we're going to take the square root of both sides. Here we go. Now the square root of something squared is just the RMS current. And the square root of 1/2 is 0.7071. And the square root of that is the maximum current. So the RMS current is 0.7071 times the maximum current. That's the current that you want. You need 12 amps to give you the same heating as a DC circuit. And so what is the maximum current? Well, let me get my calculator and we'll figure it out. Here we go. 12 divided by 0.7071. I'm getting we have to go up to 16. The maximum current is 16.97 amps. And here I'll draw you a graph of the current. It's AC. It goes up to a maximum of 16.97 amps, and then it goes down to a minimum of negative 16.97 amps. And that current there will give you the same heating as a direct current. Another name for the RMS is DC. Only it's not DC, but it gives you the same power. See, if you have 16.97 amps maximum and you go to a minimum of minus 16, that'll give you the same heating effect as the 12 amps of direct DC current. I don't know if that made a lick of sense.
Yeah, it did.
Maybe a little bit. And the same is true for the voltage.
It's alternating.
It's alternating. It's going back and forth. The same is true for the voltage. Now let me draw you the voltage. See, the voltage is the same. The maximum voltage is equal to 0.7071 times the RMS voltage. Or you could substitute DC voltage. Remember, we had a 12-volt battery. Well, you could put a 12-volt battery in here, and let's see what you'd get. 7071 times 12 volts equals no, this is wrong. No, it's 1.414. Did that wrong. 1.414. The RMS, let me do this right. The RMS voltage is equal to 0.7071 times the maximum voltage. Well, if you solve this math here, what you'll get is the maximum voltage is 1 over 0.7071, and that's 1.414.
Oh, okay.
Okay, so I tell you what that's going to be. 1.414 times 12 is, well, it's 16.97 something volts. So what you need is a volt, the volts here that goes up to 16.97 and it goes down to 16.97 volts and then back up to 16.97 volts. It'll give you the same heating, the same power as just a constant 12-volt battery. Maybe that helps a little bit.
Yeah. Yes.
Maybe a little bit. Okay. Well, I wanted to tell you about the RMS business. Now, the reason why they call it RMS is they take the root, which is a square root, of the mean of the squares. Like with the voltages, you square them. Put a little bar over here to represent the average or the mean. And so the RMS voltage is equal to the root of the mean of the squares of the voltage. The same with the current. The RMS current is equal to the square root of the mean of the squares. That's where they get the name. But the whole idea was trying to get the same power out of an alternating current that you get with a DC current. And for sinusoids, we have it. We've got the equation right here. Now be careful, that equation only works for sinusoids. for sawtooth, you've seen those sawtooth waveforms in the lab. It's different. For a sawtooth, it's 1 over the square root of 3. I think that's 0.866, isn't it? Let me see. What's 1 over the square root of 3? No, it's 0.577. This number here is 0.577 for a sawtooth. But we don't use sawtooth alternating voltage. We use sinusoidal alternating voltage. Well, we attempted to explain that. Not very good, but I tried. Let's go on and show you. Let's do a problem. Now, this is out of your book. This is problem 1569. And we're going to do it. And let me draw the circuit here. Let me find my book. And we're going to do 1569 together. Really kind of disappointed at my class. It's just you and me, Phoebe. I'm glad I've got Phoebe here, because it's no fun just talking to nobody.
I bet, yeah.
Okay, now I'm trying to find 1569. All right, I found it. It's an RLC circuit, and I'm going to draw it now. It's got a 50 ohm resistor, 200 microfarad capacitor. This is in my book on page 704. But you guys, a lot of you don't have a physical book. You just have it online.
I have both because I have to have a book.
I gotta have a book. I love books. So here, let's put the circuit on here, and we'll have a little fun. We'll do this. Now they said it's a 20 ohm resistor, so we'll put that there. And the capacitor is 200 microfarad. 200 microfarad. Inductor is 120 millihenry inductor. Okay, we got it. And it says here this has got a root mean square EMF of 240 volts. So what we have is 240 volts root mean square. Okay, there we got all the stuff. Now what do they want to know? They want to know the voltages across the resistor, the capacitor, and the inductor. Okay, well here we go. We'll do it. First thing you got to do is find the capacitive reactance. That's equal to 1 over omega C. Okay, and I'm going to do that. Well, we got to find out what the omega is. Did they ever tell us? Just a minute, I got lost again here. Let me find what the omega is. Oh, frequency is 60 hertz. Okay. They said you had 60 hertz. And you know omega is equal to 2 pi f. So if you'll do that, you got 2 pi times 60. And if you do that, you'll get 377 radians per second. So we know what omega is now. It's 377. So here we go. I'm going to take 377 times 200 e to the minus 6. I wonder if I did that right. Let me try that again. 377 times 200 e to the minus 6. Don't forget, it has you have to take the reciprocal. I'm getting 13.26 ohms. Well, let's do the inductor. Now, the inductive reactance is omega L. Well, that's it's 0.120 henries times it's 377 times 0.120 henries. Okay, here goes. I'm getting 45.24 ohms. All right, now let's draw our impedance diagram. Okay, well, we always put our inductive reactance here, and it's 45. And here's our capacitive reactance. It's much smaller. It's only 13.26. This is 45.24. And here's our resistance, which is 20, about like that. Trying to draw these to scale. We're drawing the impedance diagram is what we're trying to do. Okay, well, we have to subtract these because they're opposite. So let me do that. And I'm getting 31.98. That puts you right about here. You know what that is? That's XL minus XC. It's 31.98. And so here's your impedance. Your impedance will be the square root 31.98 squared plus 20 squared. Okay, let me do that. All right, I did that, and I got an impedance of 37.72 ohms. Now let's get this. This is called the phase angle. I think they use a symbol phi for the phase angle. This thing here is called an impedance diagram. And that's what you're going to do for me for that makeup lab. You're going to make 6 of these. And let me get this phase angle. Now, make yourself a triangle here and take the cosine of phi, and it'll be 20 over the 37.7. Let me write that down someplace. Cosine of phi is 20 over 7.72. So phi is phi is 57.98 degrees. See that angle right there? It's 57.98 degrees. It's called a phase angle. This thing right here, this cosine of phi, it's got a name too. It's called the power factor. Okay, well, we did great. Now we're going to get the current. And that's what you're going to do for 6 of those circuits. We need a little room here. How about right here? This will be good. Now, since they gave us the RMS voltage, we're going to get the RMS current. It'll be the RMS voltage divided by the impedance, 37.72. Okay, here comes the current. 240 divided by 37.72. Well, I got a current of 6.36 amperes. Now that's an RMS current. That's the same current that if you had with a battery, a direct current heater would give you the same power as this circuit here. Okay. What are we supposed to do? Let me read this problem again. That we're supposed to find that current. For all of those students out there that are watching the YouTube video, we are doing problem 1569 on page 704. And they want to know, calculate, oh, they want the voltages across everything. All right, well, we'll do that. They want the voltages, all right, here we go. If you want the voltages, a voltage across this resistor, V equals IR. All right, well, we know the current. It's, where to go? There it is, 6.36 amps. And you know the resistance, multiply it. Take that current and multiply by 20. And I'm getting put it in red. I like my voltages in red. I get 127 volts. 127 volts. That's RMS now. And we tried to talk about that. Okay, now let's get the voltage on this capacitor. Well, it's the same deal, guys. V equals I XC. Well, we know XC, it's 13 something. There it is. We know the current, 6.36. I'm going to do that. I'm going to multiply current times that 13.26. Gee, I get a big number here. I'm getting 84.4 volts. I wonder if that's right. 84.4 volts, RMS. We're doing everything RMS here. And now let's get the voltage on the inductor. Okay, same deal, guys. V equals I XL. And we know what XL is. It's right there. 45.24. And what's the current? 6 something. Well, I'm getting a humongous voltage there. Can't help it, that's what it says. I'm getting a voltage here of 200, I'll round it off, 288 volts. Gosh, that's kind of big. Now, I'm just curious to see if we got any answers, what they got. In the back of the book, they have some answers. This was problem 1569. Okay, let's go back here and I'm going to see what they said. 1569. They said, well, they got 156 volts. We're not getting any of these right. Am I on the wrong page or what? Just a second here. No, it would help if I got the right chapter. I'm on the wrong chapter. No, I'm on the right chapter. It says, they said the resistance voltage is 156. Okay, obviously I've made some kind of horrible mistake. Now let me go back. Let me go back and see where I went astray. Did I get these reactances right? I bet I did. But I'm going to check them. Here goes. Okay. Now, I got the reactance right on that capacitor. Obviously, my current must be wrong. So let me look at that. That must mean my impedance is wrong. Let me look at my diagram here again. The resistance is 20, and this is 45.24. Let me check that. I made a mistake here, and I want to see if I can find it. Okay. No, I think that's right. And then we're going to subtract the 13.26 from the 45. And then we're going to find the impedance. That even looks right. No, that looks right. And so the current should be 240 divided by 37. Well, let me try that. And that looks right. And if you multiply, surely they didn't goof up and get all wrong answers on theirs. They're bad, but they're not that bad. Okay. You know, I think I did this problem before. Let me look and see what I got. Uh-oh. Uh-oh.
Uh-oh.
Uh-oh. I wrote down 20 ohms. And that's wrong. You know what really helps when you do these problems is if you read the problem correctly. The resistance.
That happens a lot to me.
It helps a lot. The resistance is not 20 ohms, it's 50 ohms. So we're going to have to go back. Well, we don't have to start all over, but guys, I had 20 ohms there, and that screwed everything up. Now, if you read the problem, it says here, there is a 20 ohms, but it's the resistance of the inductor. See, this inductor has a 20 ohm resistance inside it. See here, I'll draw a line around. All these voltages are wrong because I've got the wrong impedance diagram. We're going to start all over. I think sometimes students learn more when I screw up than when I just do everything so right. But we're going to get it right. Here we go. I shouldn't have erased that. I think that was right. I think the 13.26 was right. And I think the 45.24 is right. But see, this I had 20 volt or 20 ohms here, and it's 50 if you read the problem. Well, that makes a difference. In fact, if you've got a 20 ohm resistor here, that makes 70 ohms, doesn't it? So look, you've got 70 ohms resistance. That's a resistance. And the inductive reactance is 45, so that puts you about to, I don't know, somewhere around there. That's 45.24. We're going to get this right this time. And then notice when I screw up, I say we are going to get this right this time. Okay, now that's supposed to be funny. Now this is 13, so let me draw that down here. It's just a little guy. XC is 13.26. Now I think we can get the actual impedance. Here goes. Well, you have to subtract those. Here's the equation. You have to subtract those, you have to square it, and then you have to add the 70 squared and take the square root. That will give you the impedance. All right. Let me do that. We're going to take the 45.24. We're going to subtract the 13.26. Then we're going to square it. Yeah. Plus the 70 squared, square root. And we get an impedance of 76.96 ohms. We think maybe we have the right impedance this time after I goofed up and wrote the wrong resistor there. But I think maybe we'll figure this out. Now we're going to get the current. Okay. Well, of course, this will be wrong too. We'll get it right here in a minute. The current, and this will be an RMS current, should be the 240 RMS volts divided by the 76.96 ohms. Okay, here goes. Hope you can read my writing. That's supposed to say 76. All right, here goes. Well, I'm getting 3.12 amperes. 3.12 amperes.
That does make more sense, I think.
Good. Excellent. I feel better now. Now we're going to get the volts across the different components. Here we go. We're getting the volts now. Well, V equal IR, that's Ohm's law for resistors. We know and love that equation. If you don't learn anything else in this course, at least you can learn V equals IR. That's valuable. So let me do that. We got the current, and we're going to multiply by the 50 this time. That rounds off to 156. 156 volts. Now let's see what they got in the back of the book there, in their answer book. Let's see. They got 156 volts. Well, how about that? We got what they got. Yay, I feel better, don't you? Now let's get this one. Yeah, that is good. Now we're going to do this one. Well, on this one, it's kind of like V equals IR. Only it's not IR because that's not a resistor. It's V equals IXC. Okay. Well, XC is somewhere here. I have it on the board here someplace. There it is, 13.26. Okay. So take your current. I got it on the board. Here we go. There's the current. Multiply by the XC. I'm going to do that. Okay, now there's the current. 13.26. Well, no, that's the XC. And the current is 3.12. I got 41.4 for the 41.4 volts for the capacitor. Now let's do the inductor. Well, it's the same deal. V equals I, but it's not IR, it's V equals I times XL. Well, what's XL? It's 45.24 times the current, which is 3.12. And I'm getting 141 volts. Now let's take a look at the answer book and see what they said those answers are supposed to be. They said, if I can find where it went here, I got lost. Here we are. That's not it. Okay. Yeah, here we go. They said that this here is 156. Boy, Joe, we got it. Uh-oh, they said that we're getting different answers again. Here's their answers. A, B, and C. For A, they got 156. I felt good about that. We got 156. That must be the resistor. Well, what is B? The capacitor. They said it's 42. And C, they said it's 154. 154 for the capacitor. Well, I don't know. 154. To get that, you would take the volts on the capacitor should be the current times XC. Well, the current is 3.12. 3.12, and the capacitive reactance is 13.26, right? 13.26. And I'm getting 41.4. Now they got 42. We got 41.4. We're kind of in the ballpark. But now let's do the inductive, the voltage on the inductor. I guess it's not 141. Do I have any room here? Maybe right here. The voltage on the inductor will be the current times the inductive reactance. The current is 3.12. The inductive reactance is 45.24. I'm getting 141. Now, what did I do wrong there? Just a minute now, hang on. 45.24. Yeah, that looks pretty good. And the current is 3.12, right? 3.12 times 30 times 45.24. I'm getting 141. Okay, guys, I think we did it right. They got it right on the part A, but you know what? I think they goofed up on parts B and C. Oh, no, wait a minute. Wait a minute. You know what they did? They included this 20 amps in this physical inductor.
Ah, I see.
And I forgot about that. Here, let me show you what's happening there. There's a little room down here. Not much.
I'm home now, by the way. I can see you.
Oh, excellent. Good. We can have a good class now. It's just you and me. Bless you for showing up. But the others, The others can watch on YouTube. It's not the end of the world. But see, what they did was they took that 141 volts, which is what I think the inductor actually has, 141 volts. And then they took the volts on the resistor. Well, V equals IR. The current is 3.12, and the resistance is 20. But see, you can't see it. It's part of the physical inductor. But see, inductors are wires wrapped around a core, and they have resistance. I'm getting a 62.4 volts on the resistor. But see, they're 90 degrees out of phase. To find the total voltage on the inductor, the physical inductor, you've got to go 141 squared plus 62.4 squared square root, if that makes a lick of sense. All right, I'm going to do that.
I don't completely follow it, but I understand it well enough to kind of understand it.
Yeah, see, they're out of phase. The voltages and the currents are out of phase in that inductor. But here we go. We're going to get the voltage on the inductor, and it's equal to 141 squared, 62.4 squared, square root. I'm getting 154 volts. Well, look at here, Shazam. You know, they were right about part C. The voltage on the inductor, we got 154 after thinking it over and realizing the inductor had this embedded resistance that I skipped earlier. But now how they got the 42 for the capacitor, you know what? I think they just made a mistake. I think they're wrong. I think it's 41.4, pretty close to 42, but it's not 42. It's 41.4. Hey, I don't think the book is perfect either. I think they make mistakes. Now, this book is pretty good. And one of the really nice things about it is the price. Do you know what the price is on this book?
Well, if you don't get the hard copy, it's free.
Yes. And that is the good part about this book. It's free. If you don't get the hard copy. How much did you pay, if you don't mind me asking, for the hard copy?
I don't exactly remember, but I want to say it was somewhere around between $35 and $45.
Well, that's still incredibly.
That's still great. Yeah.
Oh, that is great. Now, we had a book that we used for years previous to this book, and it was superior when it comes to stuff like this. It didn't make stupid mistakes like that. I think they were just dead wrong on that part B. That book, but it had mistakes too. It wasn't perfect. It had mistakes, but it was much better. But as far as the material goes, this book's got the theory pretty much the same.
And you got somebody else joining us.
Hey, really? Let's look and see here. Well, Shazam! Look here, we've got Christy and Zach. Welcome, you guys.
Hey, sorry.
I'm so glad you're here.
Hey, I didn't mean to miss out.
That's okay. Phoebe and I were having a wonderful class, and now it's going to be even better. Now, what we did, and you can watch it on YouTube, we did problem 1569 in the book. And we did pretty good on it. We got two of the answers that the book got, but the middle answer, we're off a little bit. They got 42 volts and we got 41 something volts. But I think they made a mistake on that. Well, let's move on and we'll do something else. Now, the next topic that I want to talk about is something called resonance. but I'm glad we got some more excellent students. And I was telling Phoebe, if you want to do that makeup lab, try to get that in muy pronto.
I actually had a
Actually,
question.
Yeah,
that's
go
what I
ahead,
was-
ask. I'm listening.
I actually emailed you the makeup lab, but homework number 14, you didn't put any of the problems on there. So are we still to do that, or what are we supposed to do?
Yeah.
Let me look and see. Hang on.
It just said text submission. It didn't actually say anything.
Ew. Okay, well, let me look this up here.
I'm having the same issue.
Homework number 14 was supposed to be, let me make some room here. You can watch all that on YouTube if you want. Homework number 14, and you know we're coming to the end. I think there's only one more homework after tonight. There's only one more class next Tuesday night. But homework number 14 is chapter 14, problems 57 and problem 79. So you got a couple of problems to do. And
Do you want us to do that on top of this week's homework, or like, because it's not even available for us on Black?
Wait a minute, that's wrong. That's wrong. That's wrong. Just a minute. That's all dead wrong.
I think that is right, because it's homework number 14 is the one that
We're talking
didn't
about
say anything on there.
Oh,
That is right.
No,
The
that
only way
was
I
a-
knew to do it, the only way I knew to do it is it was on the like schedule from way back, but I don't
Oh.
think it was on the like assignment page itself.
Oh, okay. Well, that's it. Now, is there a link for you guys to submit that, or will you have to do
No,
it
I
on?
don't think so.
No, because it was already due. They removed it.
Oh, that's why.
Yeah, there's several of us that have been emailing you about it because we
I
had
think
noticed it
it's-
earlier this week.
Guys, I think it's my fault. Can you do that for me and send it to me on email?
Yeah, that works.
Yep.
Do that. Okay, thank you for telling me that. That's my fault. My IT person's really pretty good about this stuff.
You may want to send out an email to the whole class because it was a discussion between a lot of the students.
Oh, okay. I'll send an email or what we call an announcement, right? I'll put an announcement on Blackboard. I don't know how to send you guys email. I can do an announcement.
If you do the announcement, it will automatically send the whole class an email, so that works.
Oh, okay. You guys are so good with this computer stuff. See, this is all new to me. When I was a kid, they didn't even have calculators. What I had was a slide rule. You guys probably never heard of a slide rule. Have you ever heard of a slide rule?
I've heard of it, but I don't remember how it works.
I still got one. But you know what? When we went to the moon in 1969, they did it with slide rules. They're pretty powerful things. Slide rules. I still got one. Okay, do it on email or do it on email. I'll announce that. Okay, now the topic right now, we're still in AC circuits, but the topic is resonance.
Did you only cover one topic before? I'm sorry for asking because I was late, but
We're still on chapter 15. Is it 15? I'm getting lost. I think we're in 15. Yeah, we're in 15. Mm-hmm. We haven't moved on. We're still in 15. And we only have one more class meeting next Tuesday after Thanksgiving. And then we'll be through. And it's been fun. I've enjoyed meeting all of you. Okay, the topic is resonance. And I'm going to do a resonance circuit here. Let me write it for you. Now here's your voltage. It's 100 sine of 314 T. This is 50 ohms. This is 0.2 henries. And this is this is 50.7 microfarads. Okay. Now what I want you to do is I want you to find the inductive reactance and the capacitive reactance. And you know the formulas. It's omega L and 1 over omega C, where omega is 314. See, that right there is your omega. All right, go ahead and find those. I'll shut up. You have a minute and a half or so, and then we'll compare notes together. Go for it.
What did the XL and the XC stand for again?
Thank you for asking. This stands for the ohms. See, those babies are ohms. They're kind of like resistance, only they're called reactance. They're opposition to AC current. And the name of it is reactance. And this little guy here is called inductive reactance. And this one is called capacitive reactance. And the bigger they are, the more opposition they pose to your AC current. Go ahead and figure those, and then we'll proceed.
What does it say on the far left? The battery. All right, I stepped away for a second.
It says 100 sine of 314 T. Can you read that?
Yes, thank you. I just want to double check.
Yeah. Good luck reading my writing.
Can they be the same number?
Yes, they came out the same, didn't they, Zach?
Yeah.
Yeah. When that happens, they call this resonance. And that's what we're studying right now. I got the same number too. I got, let's see here. What did I get? Did you get 62.8 ohms?
Yep.
This one here is 62.8 ohms. And hey, Zach, did you get 62.8 ohms on this one also?
Yep.
How about the rest of you?
I've lost my calculator, so
You're going to have to get a calculator. Hey, they have these.
Oh,
for
I have
nine-
one. No,
Oh,
I've got one.
okay.
I just don't know where I set it. So
Oh, okay. I was going to say they have these for $9 at Walmart. See this little guy I have right here. It's got everything I need for $9 at Walmart. Well, how
Yeah,
about that?
that's right.
Okay, good. Okay, now let's do the impedance diagram. Here we go. I need some room here. Yep, now you have that. It should be, maybe I need to put that on the announcements. Let me make a note to myself. Okay, now here comes the impedance diagram. This is what you're going to do on that makeup lab for me, so you can get another 10 on your lab score, and I'll replace your lowest lab score with that 10 if you don't screw up, but you won't. Okay, so what we've got here is XL, which is 62.8 ohms, and XC, which is 62.8 ohms, and then R, which is 50 ohms. But see, these cancel out. And this circuit acts like it's just a 50 ohm resistor. And so your current, now that's your maximum. That's your amplitude. If you wanted your maximum current, it would be 100 volts divided by the 50 ohms. Hey, I can do that in my head. Time to show off a little bit. I'm getting 2 amps is your maximum current. But you'll discover everything in AC is in RMS. You guys missed my wonderful RMS explanation tonight, but you can watch it on YouTube. Yeah. And here's how that works. The RMS current is equal to 0.7071 times the max current. So if you'll multiply 2 times 0.7071, I think you get 1.414 amps. That's your RMS current. And like I explained in my wonderful but confused explanation earlier tonight, if you had a DC current equal to 1.414 amps, you'd get the same power. You could run this circuit with a battery, a DC battery, and get the same power if you had a DC current equal to 1.414 amps. But when you have AC, they call it the RMS current. It's a root of the mean of the squares. It's the square root of the mean of the squares. You take the squares of the currents, which the current changes. It's small, it's big, it's small, it's doing this. It's changing not only in magnitude, but in direction. But if you take the mean of it, they call it the root of the mean of the squares. And that's it. Now we can get our power. Here we go. The power.
Where did the 0.7071 come from?
I'll try to show you. I'll try to review here. You know, you have this current that's AC current, and you understand that. And then when you square it, see, that's the current. You understand that's the current. When you square that current, what you'll get, Christy asked this question, we're going to try to answer it. When you square it, if it's 0 and you square 0, you get zeros. That makes sense. Now, when the current is negative, see, it's negative here. It's going the other way. But when you square a negative, you get a positive, right? Negative times a negative gives you a positive. So if you try to draw the square of the currents, here's what you'll get. You'll get a peak. You get a 0. But you get a positive peak. You get a 0. You get a positive peak. A 0. Positive peak. A 0.
So is it just a constant?
Well, what we're doing here is we're plotting I squared. See, when you square 0, you get 0. But when you square this maximum current here, you get a square of it.
Yeah, I understand what you're saying with all that, but I'm the 0.7071. Is that a constant?
Yeah, it's a constant. And
okay.
And here's where it comes from, Christy. The average of these squares is right smack down the middle. That kind of makes sense. I would say the average of that is right smack dab in the middle. And so the average of the squares is 1/2 the maximum current and of the squares. It's 1/2 of the squares. Another way of writing this is the RMS current the current squared, the DC current squared is 1/2 the Imax squared. And so if you take the square root of both sides, what you'll get is there room to write here? Not much. They don't call it the DC current, they call it the RMS current. What you'll get for the RMS current is the square root of 1/2 times the maximum current. What this is the DC current that will give you the same power, the same heating effect if you had a heater, for instance. And the square root of 1/2, do it on your calculator. It's 0.7071. Christy wondered, well, what the heck is that 0.7071? It's a constant. And here's the equation. The RMS is 0.7071 times the maximum. Okay, so we got it. We got the RMS current. And now we can get the power. Here goes. I need some room here to get the power. There's some room over here. Well, power is just going to be the RMS current squared times the resistance. See, this is the average power. And the average power for the inductor is 0. Now it has power, instantaneous power. It stores up energy in the magnetic field, but it gives it back to you. Stores it up and gives it back to you. In this case, it turns out to be 50 times a second. That omega is equal to 2 pi times the frequency. And if it's 314, this is what they have in Europe. That frequency turns out to be 50 hertz. everything's 50 hertz over in Europe. But see, every 50th of a second, the inductor stores up energy, gives it back, stores it up, gives it back. And so the average is 0. And the same with the capacitor. The capacitor stores up energy in the electric field. Every 60th of a second, it gives it back, stores it up, gives it back. The average power in the inductor or in the capacitor is 0. But the resistor doesn't give you any power back. It doesn't store power. It just gets hot. And here's the power. It's equal to 1.414 amps squared times 50 ohms. Do that with me and we'll get the power of this circuit. Go for it. 1.414 squared times 50. I'm getting 100 watts. How about you guys? I'm waiting to hear an uh-huh.
Yeah, I got 100.
Yeah, well,
99.1. So
I
yeah,
got
that's on.
I got 99.9, blah, 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 but let's just round it off to 100 watts. This
So-
circuit has an average power of 100 watts. Now you can do,
have a question?
go ahead.
I was trying to figure out when he was going to use where did you already use the square root of the mean of the square or the root of the mean of the square? When we were talking about that.
In order to get the RMS current, we use this right here, Zach. And
Okay.
it's equal to 0.7071 times the maximum.
All right,
And
I guess.
that came from this business down here.
Okay.
Now we can get this average power a couple of other ways. Let me show you. I just need some room here someplace. We'll make some room. Since the inductive reactance and capacitive reactance cancel out, we can get the average power by doing this. Take the RMS voltage, square it, and divide it by the resistance. We should get the same power. Let's see if we do. Now you understand that that's the maximum voltage there. That's the maximum voltage. And here's how it works. The RMS voltage is equal to 0.7071 times the maximum voltage. Well, if the maximum voltage is 100, well, then the RMS voltage is 70.71, right? So put it in there. Let's try it. 70.71 volts, square it, divided by 50 ohms, and tell me what you get. Go for it. Boy, Jew, I think when you do that, you come up with 100 watts. If you got 100 watts, say, uh-huh.
Yep.
Yeah.
Yes.
Yeah. Well, there's a third way to do it. And let's do it a third way. I just need some room here someplace. Now, you've worked with these equations before. It's just that you didn't work with a AC circuit. But you can also get this by going P equals IV. But they have to be RMS. Now the RMS current is 1.414 amps, and the RMS voltage is 70.71 volts. Those are the RMS values. And that's what you measure in the lab when you take your voltmeter or your ammeter, your AC voltmeter or your AC amp meter. That's what you always measure. They don't measure your. Go ahead.
Are we having lab Thursday?
No, ma'am. We are.
It's Thanksgiving.
Yeah. That's
I feel
fine.
real smart now.
Hey,
Can you, where
I
did you?
I say things like that all the time, and my wife was so gracious. So she didn't tell me I was a stupid idiot here this afternoon when I said something stupid. We all say
Uh,
stupid stuff.
But we're not having labs anymore the rest of the semester, right?
We are done, done. We won't ever see each other again, and it's sad. It's sad because we had so much fun. Unless I meet you walking down the street sometime, that'd be okay. Hey, Mr. Griffin. Hey, Christy, or what, whoever. But no, we're done. And I don't
So,
know if I've told you guys the sad news is I'm retiring. Did you know that?
Oh,
I don't think you told us that.
I'm so sad for you guys. I would love to have you again, but I'm out of here. I've been teaching now for close to 50 years, so maybe it's time, don't you think? I'm 77 years old. I got all these grandkids, and I've loved my job, and I hate to leave it, but I think it's time. So I'll be out of here. You guys will have another wonderful instructor, and we've got some great ones. We really do. Okay, now multiply that. I'm showing you this other formula, and tell me what you get. I'm hoping it'll be 100 watts, is it?
basically.
Yeah, let me try it. 1.414 times 70.71. Boy, Jove, it's dang close to 100 watts. I got 99.9 something. And you're familiar with those equations. Now watch it. Those equations only work because we were in resonance. And what is resonance? Well, it's when XL is equal to XC. So here, let's just play with that formula for a minute, and then we'll do another problem. I just need some room here. I'm going to have to erase some of this stuff. Yeah, now I got some room to work here. Now, XL is equal to omega L. XC is equal to 1 over omega C. And then we're going to set them equal, and we'll have resonance. So we'll have omega L equals 1 over omega C. Now we're going to do a little math here. See if you can follow this. Can you get to here? I bet you can. And then we'll do another little math trick here. Can you make it to there? Now let's see what the angular velocity is. Some books call that the angular frequency, which is okay. You can call it that if you want. Let's see what it is in our circuit. If L is equal to 0.2 henries and C is equal to 50.7 microfarads, I'm going to shut up for a minute and a half. I want you to plug those in and take the square root and tell me what you get. Go for it.
314.
Well, that's what I got. Now, what are the units on that 314?
Well, if it's angular velocity,
Yes.
I'm really not sure.
It's radians per second.
Oh, okay.
It's radians per second. Well, that's what we got. That's why this is a resonant circuit, because we have the resonant frequency. Well, let me show you the resonant frequency. Omega is equal to 2 pi f. And if omega is 314, get your calculators and solve for the frequency. Go ahead.
I got 49.97.
Let's just call it 50. We'll round it off. We'll put a little squiggle here. We'll call it 50, and that's hertz. And remember what a hertz is. A hertz is a second to the -1. Well, that's what they have in Europe. If you had this circuit in Europe and you plugged into the wall socket in Europe, you would have a resonant frequency. But if you had this circuit in the United States, it would not be a resonant frequency. I think it'd be fun to do this same circuit in the United States. Don't you think that'd be fun? Yeah, Mr. Griffin, would be fun, yeah. Okay, well, let's do it. Here, let me erase all this so we'll have some room to work. Let's suppose you had the same circuit, but it's in the United States. You could still have the 100 volts max, but see, in the United States, the angular velocity is 377. 377. Because, see, in the United States, it's 2 pi times 60. The frequency of our AC circuits in the United States on our power grid is 60 cycles per second, not 50 like it is in Europe. And so if you'll multiply that, you'll get 377 radians per second. Let's change this. Now we've changed this. We still have 100 sine of 377t, and we're going to work this problem here now. This will be fun. You'll love it. Here we go. What I want you to do first is I want you to find the inductive reactance and the capacitive reactance if you had the same circuit in the United States. On your mark, get set, go. Here, I'll write the equation in case you forgot. And see, we've got the C, and we've got the L, and we've got the omega. I know you can do this. Go for it. Okay. Well, I got some answers here. When I did this, check me, make sure I got this right. Did you get 75.4 ohms for the inductive reactance and 52.3 ohms for the capacitive reactance? If you did, say
Uh-huh.
Uh-huh.
Yeah, we're doing great. Okay, now I want you to draw the impedance diagram. I'll be quiet again for a minute. I want you to draw the impedance diagram, and I want you to find the impedance. They use this symbol Z for impedance. Draw the diagram, find the impedance. I'll shut up and let you work. Go for it. Okay, I'm going to put this up here, and then we're going to take a 10-minute break, and I'm going to go see what's in the refrigerator. But here comes your impedance diagram. You got 75.4 ohms, and then you have the 52. .3 ohms, and then you have a 50 ohms. You have to subtract these, and when you do that, you get, I think, 23.1. That's XL minus XC is 23.1. And here's your impedance. You have to square 23.1 and 50. And I did that. And I wonder if I did this right. I got 5508 ohms for the impedance. If you got that, say uh-huh.
Uh-huh.
There's two of us. There's three of us. I bet I did it right. Okay, now look, we're gonna find the currents, and we're gonna find the power in this circuit, and we'll have some fun with this circuit here in a little bit. But right now, we are going to take a 10-minute break, and I'm going to go look in the refrigerator. We'll be back. We'll be back in 10 minutes. Go stretch. Go stretch. We'll be back. Well, welcome back, everyone. I fed our dog. She was quite happy about that. It's not raining right now. She's an outside dog. We got her at the pound 12 years ago. She's a rescue dog. But she's plenty smart. Okay, we had this circuit a while ago, but we had it at omega was 314. It was a angular velocity in Europe. But see, the angular velocity in the United States, 377. So we moved this circuit to the United States. And we've come a long way. We've got the reactances here. I put them right there. We found the impedance. Hey, we can get the current, and then we can get the voltages. Let's do that. Okay, here goes. We're going to get the current, and we have our faithful three here, the tres amigos. All right. Here we go. The current is, now this is going to be the RMS current. Remember, this is your maximum voltage. To get the RMS current, you need the RMS voltage. And the impedance is 5508. And so the current is I got 0.7789 amperes. And now with that, we can get the voltage on each component. Here's how to do it. V equals IR. V equals I XL. Can't seem to write tonight. V equals IXC. Go ahead and get those, and I'll put them in red on our circuit diagram. I'll shut up while you guys get those voltages for me. And we'll get the voltages. Here we go. Okay, here's what I got. I got 38 0.95 volts on the resistor, 58.73 volts on the inductor, and 40.74 volts on the capacitor. Those are RMS voltages. If you got those, say uh-huh.
How did you get the first one again?
Thanks for asking. I took the current, which we think is, where to go? Oh, here it is. The 0.7789 amps, and I multiplied by 50 ohms.
Oh, I did the wrong resistance. Okay.
But thank you for asking. Are we all squared away with those, you think?
Yeah.
Great. Great. Now let's get the power. I want you to notice something, though. We don't have resonance. See, resonance, remember, is when XL is equal to XC. We don't have resonance. XL is 58 and XC is 40. How come we have 75 and 52? I'm getting confused here. Oh, no, never mind. I'm fine. That's the voltages. XL is 75 and XC is 52. We got it here. We did everything right. These are the voltages. But these are not equal. 75 is not equal to 52. Let's put an unequal sign in here. There we go. The reactances are not equal. We don't have resonance. Now, this angle right here, they've got a name for this. It's called the phase angle. Let's get it. It's called the phase angle of our circuit. Now, I'm going to shut up. We know everything there is to know. We know the R, the Z, the XL, the XC. I want you to find it for me. Find the phase angle. I will shut up for 1 minute. Can you find the phase angle? Do it.
$65 degrees. 65.2.
I didn't get 55.
I
I
said 65. 65.
I didn't get 65.
I got 24.8.
I didn't.
Oops, sorry.
Well, you're forgiven. I got 24.8. Zach, how did you do that?
I did the inverse cosine of 50 over 55.08.
That'll work. The cosine of phi is equal to 50 over 55.08. You can get it that way. Or the tangent of phi is equal to 23.1 divided by 50. That should give you the same angle. Try it. Try it. Take 23.1 divide it by 50, and hit the inverse tangent. Boy, Juve, you get 24.8. Or the sine of 23.1 divided by 55.08. The sine of phi is equal to 23.1 divided by 55.08. You could do it that way. Now let me try
I know
that.
what I did now. I'm sorry.
I think I know what you did. You got it upside down.
Yeah, I mixed up my sine and cosine.
That's what you did, yeah. I think you got the complement, though. If you subtract yours from 90, you get the right answer.
Probably.
But if you try this, let me try that. 23.1 divided by 55.08. The inverse sine. Boy, Jove, you get 24.8. We've got the phase angle. Now let's get the power in this circuit. I just need some room here. Let me write this current down. Well, I have it in my calculator. Just need some room to work here. Now, one way to get the power in the circuit is to take your RMS current and square it. I squared R. P equals I squared R. You've seen that before. I think we've used it before. And see, the current is 0.7789 amps. And you square it and multiply by your 50 ohms. See, the others don't give you any average power. We're talking about average power. Remember my little sermonette about they give and they take? They give you energy and they take it back. The inductor stores energy in the magnetic field, but it gives it back to you. The capacitor stores energy in the electric field. They store it up, they give it back. The net result is zero. But if you do this, you'll get the resistor doesn't give you back any, it just gets hot. And if you do that, you can get the power. Go ahead and do that and tell me what you get. We'll pick on somebody. Christy, have you figured out what this power is?
I do not. I was just talking to a client, so I'm way behind.
Oh, that's okay. You can watch the YouTube if you want. How about my friend Zach? What'd you get, Zach, for the power?
30.33.
That's what I got. I got an average power of 30.3. That's fine. What would be the units on that power, Zach?
Watts.
You got it. 30.3 watts. Now there's another way to get this. Let me show you the other way. I need some space here. We'll sneak in.
Sorry, can I interrupt for a second before you erase?
Yeah.
The IRMS that's squared.
Yeah.
Where
Yeah,
did
you
that
have
come
to
from?
square
Did I
it
miss
once.
where that came from?
Oh. Well, we got the current by dividing the 100. Here, let me write it out for you.
Okay.
We got
Sorry,
the,
that might have been what you just erased.
That's fine. The RMS current, we got that by taking the RMS voltage and dividing it by the impedance. the impedance was 5508, and I bet you're okay with that.
Yeah.
See, but this here 100, that's a maximum. That's not the RMS. There's an equation for RMS. It goes like this. The RMS is equal to 0.7071 times the maximum. So see, this is 70.71 volts, and you divide by 55.08 ohms, and you'll get 0.7789 amps. Then you square
Okay,
it.
thank you.
Yeah, anytime. Anytime. All right, now let's see. I wanted to show you another way of getting the average power. It's an important equation. It's in your book. Let me see if I can find this equation. The equation I'm talking about is this equation here. And that equation is on page 685 in your book. See, this book isn't so bad. That equation's there. It's just that you have to know that those are RMS voltage values. It's in your book. I didn't make it up. But let's try it. Here we go. We're going to try that equation. We're going to solve for the average power using this equation here. It'd be fun to derive that equation. This is 0.7789. This is 70.71. And then this is 24.8 degrees. Put that in your calculator and tell me what you get.
I got 50 degrees. Oh, well, no, not degrees, but 50.
Let me see what I get. Boy, Job, I get 50. What did we get?
How did you get that?
We have a problem. Houston, we have a problem. The answer is supposed to be 30, and we're getting 50, Zach. I'm getting 52. I did something wrong. Now let me see what I did wrong.
You're taking 70.71, multiplying it by the cosine of 24.8 degrees.
Yeah, at times 0.7789. Let me do it again.
Oh, times 0.778. Okay.
Yeah.
Yeah, I got 49.99.
Okay, now just a minute. Now I've done something wrong. I'm coming up with 50, not ohms, watts. And this should come out with the same. Oh, no. This is wrong. This is wrong. This only worked when you had the resonant circuit. Remember our resonant circuit? Now, this equation right here. Maybe it's good I did that. This is a nice little equation if you have resonance, but we don't have resonance. We don't have, but now wait a minute. You should still get the same power because all the power is used by the resistor, right? Now I'm getting confused, guys. Just a minute now. Let me think this out. Let me try this. I'll figure this out, hopefully. This should give you the average power. We know the RMS voltage on the resistor is 38.95 volts. Square that and divide by 50 ohms and tell me what you get. Let's try that.
That's 30.3.
All right, that's 30.3. What did we get when we did this?
30.3.
We got 30 point. Did we?
I mean, that's what I wrote down.
No,
Why did you change the V? Why is your VRMS 38.95 instead of 70.71?
Oh. Well, this is the voltage of the source, Zach. See, that's the source. But the resistor is not the source. It's 38.95, right? And when you square that and divide by the 50, the 38.95. Okay, right now, guys, I'm kind of confused, but we'll figure this out. We get 30.3 watts that the resistor is using, and that should be the same for the whole circuit. Now, for the whole circuit, the current in the whole circuit was, where'd it go? We think it's 0.7789. The voltage of the source is 70.71, and we think the angle is 24.8. But that gives us 50 watts, doesn't it? There's something terribly wrong here. And I made a mistake someplace. This has to come out the same. So let me check it and see what happened here. Maybe you can find my error. I must have made an error. No, this is the impedance. I think that's right. And if you take, if you want the current, it should be 70.71 for the RMS current, should be 70.71 volts divided by the 55.08 ohms for the impedance, and that is 1.284 amperes. These amps that we're playing with here are wrong. I don't know. Does anybody know where the heck I got that? The amps, the root mean square amps I'm getting is 1.284 amperes. See, when you divide this, you don't get 0.77. Where the heck did we get the 0.77? It must be a calculator mistake. You know what that is? That's the reciprocal of 1.28. Now, I bet if you take 1.28 and multiply by the voltage times the cosine of your phase angle, let's see what you get. This was wrong. I had the wrong current. Put in the right current and let's see what happens. Okay, now just a minute now. 1.284 times 70.71 times the cosine of 24.8. Well, I'm not getting the watts that we got at all. There's still a problem. I'm getting 82.4 watts. That can't be right. Okay, I've made a mistake, guys. Let's see if I can figure this out before time is up here. Oh, I think here's the problem. I'm sorry to put you through all of this agony, but see, this voltage is going to be wrong. If that current is 1.284, and I think it is, see, if you take the volts and you divide by the impedance, you get 1.284. You don't get 38.95. That's a screw up. Okay.
Oh yeah, we got to redo all our votes again. Don't we?
All these volts are wrong. They're all wrong, and it's my fault. And I humbly apologize, but we're going to get it right here eventually. We're going to take the right current, which is 1.284 amps, times it by 50 ohms. And here's what you get. Now this should be correct. 64.2 volts here. Now let's get the volts here. You take the correct current this time, which I think is 1.284, and you multiply by 75.4. I think we got that part right. And I'm getting 96.8 volts there. Now let's get the volts here. If you take the current, 1.284 amps, and multiply by the 52.3 ohms, you get 67 point, I don't know, round it off to 2 volts. There you go. Now let's get the power, and let's get it correct this time. Take that 64.2 volts and square it and divide by 50, and let's see what we get. 64.2 divided by 50.
82.
Boy, Jove. 64.2 squared divided by 50. Boy, Jove, you get 82.4 watts. Well, look at here. 82.4 watts is correct if you put in the right current. I just got to learn how to divide. See, that's my problem. When you divide 70 by 55, you don't get 0.88 or whatever we got. You get 1.28. And so we have our volts correct now. We have our impedance correct. We got our power correct. There's a third way to get that power on the resistor. Do we have room to do that? We'll make room.
Does it matter that when I do the first, like the I RMS squared times R, when I do that way, it's slightly off? Does that matter? Like it's like the bottom equation is 82.4 and the top equation I'm getting 81.92.
Well, did you take 64.2 and square it?
Yeah, you and I have the same exact thing for that one. The equation right above it that we had wrong the first time. Nope, left.
This one?
Left. Nope, far left. Power underneath the whole thing.
This
yeah, right
one.
there.
Okay, take the 1 point, where'd it go? The current. Well, take the 1.284. Take the 1.284 and square it. Let me do that.
That was my
Square.
problem. I missed the 4.
Ah, the 4. Square it and then multiply by 50. By Jove, you get 82.4. By Jove, it works. There's a third way, and I think I have room right here, maybe. The important thing is that all the power is being used by the resistor. The other two components, they use it if you just look at a tiny fraction of time, but over the whole time period of a period or two, they don't use any power. But the other way, for the power of a resistor, you can just go I RMS times V RMS. It should give you the same amount. Well, what is the I RMS? Well, that's the 1.284. And what is the V RMS? That's the 64.2. Multiply that. Let's see what we get. Times 64.2. Boy, Jove, you get 82.4 ohms. Now, wasn't that fun?
Watts.
I didn't write it. But I'm going to give you a thank you point anyway, because I said it, and it wasn't ohms, it's watts, isn't it? Hey, you're awake.
It is.
You're awake. I really appreciate students that stay awake.
I'm a night owl. I come to live as it gets later.
Okay. Well, I'll tell you what let's do. We're going to change this circuit one more time. I'm going to change it one more time. Let me think about this. Let's change it just a little bit. We're going to change it. Remember, we had it in Europe. We had the 314, and now we did this circuit in the United States, and we had an omega of 377. And we got all the answers. We figured everything out. We figured out phi, the whole ball of wax. But let's change that angular velocity. What we're doing is we're changing the frequency. We'll change it a little bit here. I'm going to erase all this stuff, and we'll keep the things that haven't changed. The circuit hasn't changed. The capacitor is still, it's still the same. It's 50.7 microfarads. You don't change it. Now the voltage is going to change here in a minute, because we're going to change something. But the 0.2 henries, that doesn't change. The 75.4 ohms is going to change. And the 64.2 volts is going to change. But the 0.2 henries doesn't change. And the 50 ohms doesn't change. Here, let me show you what I want to change. Don't want to erase that thank you point. We'll do one more circuit here. And this time I'll try not to get the wrong answers like I just did. We're going to change this frequency. We've changed it once already. We had 314, and that's 377. let's change it. See, at 314, we had resonance. At 377, we do not have resonance. The only angular velocity that gives you resonance is a 314, and we changed it. Let's try something kind of in between. Maybe how about 350? We're going to change this to 350 T. We'll keep the 100 volt max, but we're going to change the omega. To 350, what amounts to radians per second. That's going to change the XL. It's going to change the XC. It's going to change the impedance. It's going to change the current. It's going to change the phase angle. And I'm going to shut up and I'm going to let you get those. And we'll do that together. Now, this will not be a resonant circuit, but we just did a circuit that wasn't resonant. Resonance. All right, I'm going to shut up. I want you to get that, and that for me. Go for it. Well, it's very helpful to get these. I got 70 ohms for that one and 56 0.35 ohms for that one. Now for the impedance, I got 51.83 ohms. If you got 51.83 ohms, say uh-huh.
Uh-huh.
Yeah, well, gosh, you guys are fast. Good going. Now we can get the current, this will be the RMS current. So you're going to have to take the RMS voltage and divide by your impedance. Well, that's 70.71 volts divided by 51.83 ohms. Did you get a current of 1.364 amperes?
Yes.
Yay! Proud of you. You guys are, you're going to do great. And now this is called the phase angle. And I showed you 3 different ways to get it. I think I used cosine. But I got a phase angle of 15.27 degrees. Anybody get that? Hey, we're doing great. We're doing great. All right. Now let's get the power. Now the power, we're talking about average power. Because remember, the instantaneous power varies from plus to minus, and it varies in its amount. Because see, the instantaneous power is equal to I squared R, and the current is varying. It's a sinusoid. It goes one way, it turns around and goes back, it changes direction. So the instantaneous power is changing all the time, but the average power isn't. And we have several equations. Now, one of them goes like this. You take the RMS current, you square it and multiply by R. That should give you the average power. Go ahead and get that, and let's see what that is.
I got 93 watts.
Hang on, I haven't got it yet. I'm working on it. You take the RMS current and you square it and you multiply by 50. I got it, 93. Good going. 93 watts, good going. Now we can get that average power another way. Let's do it this way. I think I hear rain. I think it's raining here at my house. We can get it this way. Oh yeah. I definitely hear rain. Well, let's see if this works. Now the RMS current is 1.364 amperes. And the RMS voltage is 70.71 volts times the cosine of 15. All right, let's do that and see what happens. Try that. By Jove, I'm getting 93. This time I got 93.04. But let's don't change our majors just because of that 04 instead of the 06. I think it's a round off type deal. See, when you're inputting 4-digit numbers, and you get 4-digit accuracy, the last digit is a little bit shaky. You know, you've studied that, I hope. They call it significant figures. If you input 4 significant figures, the last figure is shaky. Hey, we got the average power. We did great. We did good. Okay, well, good going. Now, what did we get for the power on the other circuit that we erased? Does anybody remember? We got average power. Dang it, I erased it.
It was 82.4.
Did we get 82.4? On the one we just did at
Yeah, the power was 82.4.
82.4?
Yeah.
Well, we're getting more power here somehow. Now, how are we getting more power? You know what? I think we're getting more power because we're getting closer to a resonance. Now we don't have resonance. Look, 70 is not equal to 56.35, is it?
No.
No, so we don't have resonance. Remember what resonance is.
XL is equal to XC.
Yes. That's what resonance is. Now to get resonance, this has to be 314. Now when omega is 314, then you have resonance. What was the power, the average power at resonance? Does anybody remember? I can tell you what it was. You forgot? I can tell you what it was because, say again?
100 watts.
Thank you so very much. I think you're absolutely right. Because, see, at resonance, you can use this equation here. And if that's 70.71 and you square it and you divide by 50, I think you get 100 watts. Is that right? Let me try it. 71, square it, divide by 50. Now, what did I do wrong? 70.7.
Yeah, I got 99.998.
There you go. Yeah, me too. Now at resonance, we got 100 watts. Now, let me draw you a little diagram. They do this in your book. Let me see if I can find this picture in your book. This is chapter 15, right? Yeah. We're in chapter 15. And the topic tonight is resonance. I just need a little room here to operate. We'll make room. In your book on page 689, they have a graph of well, basically power divided by frequency. They have a graph of power divided by frequency. And they have this graph like this. You'll see it in your book. And this right here is your resonant frequency of 314 radians per second. Now, what we did with the European one, what was this for the European one? Do you remember? I can figure it. It was
Which one?
the second one we did. It's 2 pi times 50 is what it is. It's 2 times pi times 50. It was no, we did the 314. That was resonance. You get your maximum power, and you know what it is? It's 100 watts. You get your maximum power at resonance. Now, what we did, what was the last one we just did? It wasn't 315. What was it?
377.
Yeah. Yeah, it was, thank you so much. It was 377. And what did we get for the power on the 377? What was it?
82.4.
Yeah, there we go. It was about here maybe. At 377 radians per second, we got, what'd you say, 83.4?
82.4.
Thank you so very much, 82.4. And now we did this again. We just now did it again at 350. Well, see, 350 is kind of right in here someplace, right? And so it should be somewhere in here. What do we get for the power at 350?
93.
There we go. Yeah, there it is, 93. Good going, 93.04. You know what? We did this at 3 different places. This one here is called resonance. And see, when you tune in your radio or your television, any kind of a receptor in electronics, if you can get it to the resonate, you'll get your maximum power. Anything else that's not resonating, you don't get the maximum power. It's kind of interesting. If we had time, it would be fun to plot some over here, but I don't know. I'm kind of getting bored with this. But see, over here someplace is I don't know, maybe see, this is 314. That puts you right at the top. And somewhere in here you get your you would have 50 watts. It would be fun to find where that is. That's called a half of your maximum power. And my guess is it would be somewhere in the ballpark of taking a wild guess here. Probably around 240 or so. If your angular velocity was around 240, you should be somewhere in the ballpark of 50 watts. I wonder if we had time to do that. But if we had time, it would be fun to do that. But see, this has got a name. You see this distance right here? They call that delta omega. It's called the bandwidth. I bet you've, how do you spell bandwidth? I guess it's like that, just
WIDTH.
Is it W-I-T-H? Width?
WIDTH.
Oh, yeah. Thank you so very much. You're absolutely right. It's bandwidth. See what the bandwidth is when you connect the 2 places that have half the maximum power. See, the maximum power was 100 watts. And half of the maximum power would be 50 watts. Well, if you connect those 2 places here, they call that the bandwidth. And they have an equation for it in your book. And I wonder if we can find it here. Well, we can get it from this equation. It's roughly the bandwidth is roughly R over L. Let's see what that is in this case. Now the R is 50 ohms, and the L is 0.2 henries. Now remember what a henry is. A henry is equal to an ohm times a second. So the ohms cancel, and what you wind up with is seconds to the -1. Well, that's what angular velocity is. It's radians per second. And in this case here, what's 50 divided by 0.2?
20.
I think it's 250, isn't it? What's
Yeah.
50? 250. So if that equation is right, and I got that equation on page 689, you have to do an algebra step to get it. So if this here is 250, then half of it would be 125. So what's 314 minus 125? Well, it would be
189.
well, thank you so much. Right here, I'm wrong about the 240. It's more like 189. And this value here for the 50 watts here, you would add the two. And when you add those, you get 439. 439. It would be fun to take those angular velocities there and see if you get a bandwidth of 250 radians per second. But at least you've encountered the idea of the bandwidth. And when you go and buy a piece of a receiver of some kind, the best kind are these that have a very narrow bandwidth. Because see, if they have a too wide a bandwidth, you might pick up two stations at the same time. Now, like at night, radio signals bounce off of the ionosphere, and you can pick up WLS in Chicago. And you're listening to your radio, and you hear some announcer advertising cars or something up in Chicago. You hear two stations at once because your radio doesn't have a very narrow bandwidth. But see, if the bandwidth is narrow enough, it'll block out any other stations at these other frequencies, and you'll only pick up the station that you want to hear. But the trouble is, receivers like that cost more money that have narrow bandwidths. Well, that's kind of interesting, and there you have it in your chapter. Well, we've had a fun time tonight, and we'll meet again next Tuesday night at 5:30, and we're going to wrap up the semester. I'd like to kind of have a review of the semester and hit some of the highlights and show you how some of this relates to the speed of light. That should be interesting to you. Do you have any comments or questions before we say goodbye for the Thanksgiving vacation?
I did. I just wondered, whenever we do our final after we come back. So, because we come back and we have like what, 1 or is it 2 weeks and then the final?
We're going to have this week, and it's Thanksgiving vacation. Then we'll have next week, and there's classes next week, and we'll have our wonderful lecture at 5:30 on Tuesday night. And then the following week is finals week, and you'll be given your final, I think, on that Tuesday night. And you have 3 days to do it in. It's a take home, do it at home. Of course, we do everything at home, right? Did that answer your question?
Yeah, it did. And then I guess you're just gonna post it on Blackboard like you do the homeworks and everything?
Yeah, yeah, it's going to be on Blackboard, just like your homework.
Perfect.
Anything else from anybody? Well, okay, it's been fun. And I will see you next Tuesday night. Hopefully we'll all be safe and
I have
sound.
a question.
Yes.
I'm sorry. So I don't know if this was something that you would consider doing, but do you think we could have a review for a final next week when we would normally have lab? Like an online one?
I'll tell you what I'll do instead, Phoebe. We'll try to review next Tuesday night.
Oh, okay.
Yeah, that's what we'll do.
Alrighty then. Thank you. Have a good
Okay.
Thanksgiving.
Thank you. You too. We'll see you guys. Bye-bye.
Bye.
Bye.
Bye.